o bom? Ou estão...
Sí, está en modo presentación, profesor.
Okay.
It is okay, sir. This is okay.
Let's start again, please.
Yeah, sure. So now already time it is gone. Okay. Yeah. Good morning to all. Is audible, sir? Yeah.
Yeah.
So is it? Yeah. Fine. Yeah. Good morning to all. Myself, Dr. Narsi Boya from India. So today I'm going to discuss about the green synthesis of metal nanomaterial and their application, photocatalytic activity for the remediation of the environmental pollutant dyes. Yeah. So next slide. Yeah, please next. Yeah. So introduction. Nanomaterial defines the material that size should be nanomaterial, that is 1 to 100 nanometer. If it is 1 to 100 nanometer, more nice. Yeah. If it is 1 to 100 nanometer, that is called as a nanometer. If it is more than 100 nanometer, that is as a bulk material. In the modern size, nanotechnology more and more interested in the research field because it is huge number of application and different types of nanomaterials. So nanomaterial, that is a quantum dots, lipomers, and carbon nanotubes, and gold nanomaterial and functional nanomaterials. Why it is using for the nanometers? So nanomaterial shows the medical properties and thermal properties and electrical properties and magnetic property and reusability also it is there. So nanomaterials see huge number of applications, that is the environmental application and solar energy and sensor applications and photocatalytic activity and biological applications. Yeah, please go on for the next slide. Yeah, synthesis of nanomaterial majorly two methods, that is the chemical method and green method. While we are looking for the chemical method, require the high temperature and reaction process very slow, and reaction is very several process, and reducing is costly and hazardous. While we are looking for the green method, is non-toxic and simple and low cost and high stability. And synthesis of nanomaterial, it is a plant, it is cheap and eco-friendly to the nature. So that reason we are looking for the synthesis of metal oxide nanomaterial green methods, that is the called plant extract. Yeah, please. This is the toxin. Yeah, please. Next. Yeah, this is the taxonomy. Kingdom is Plantae, under its Malvasia, and botanical name is Gospium barbidans. While plant material, once we are seeded it to plant, it is take 5 to 6 months. Once it is 5 to 6 months, cotton process it is taking. So then once it is completely plant material, waste material. So that waste material we are it is material that is used the synthesis of nanomaterials. Whether it is any responsible for the chemical, it is there is responsible for the polyphenols is there or not, we are going to check in the cotton piece. Yeah, next. Yeah, so this is the picture. Actually, once it is cotton peels collected, that material, so that plant is completely waste material. So that is the other waste material. So they are burned in the land itself because it is so they are cultivating the another crop. So farmers, they are burned in the land itself. So then they're cultivating another crops. So that reason we are looking for the synthesis of nanomaterial completely waste material. Yeah. So initially we are going for the looking for the whether it is any phytochemicals is there not, preliminarily we are checking. So that is the polyphenols and flavonoids and carbohydrate and amino acids and alkaloids which is present in the plant extract, that is so in the cotton peels which is present. So these are the responsible for the formation of the metal oxide nanomaterial and metal nanomaterial. Yeah. Yeah. So Okay, this is further we are confirmed for the phytochemicals by HPLC, high liquid chromatography. This is the chromatogram. So this is the chromatogram. So the chromatogram which is 4 or 5, which is peaks. So which is matches with the standard ascorbic acid, gallic acid, pyrogallic, ellagic acid, which are the phytochemicals present in the plant extracts. So these are the functional groups. So responsible for the formation of the metal oxide nanomaterial. Yeah. Synthesis, this is the synthesis process, how we are going to synthesize the metal oxide nanometer. So that is the tin oxide nanometer. We are developed the material by using the plant extract. So this is initially we are taking the tin chloride. So tin chloride dissolved in 30 ml distilled water. Then we are added to the extract. So that extract, how we are synthesized the extract, how we are extracted. So that ball pills, that is empty ball pills, that is grinded. So then grinded that we are making the powder. So that powder, fine powder, we are made in 3 grams in 100 ml. So 3 grams in 100 ml we are dissolved into the double distilled water. So then dissolved in double distilled water, we are making the we are making the heating. So then heating, it will be so completely it is phytochemicals dissolved in the waters. So then we are filtered, and remaining positive waste and extract it is we are collected. That extract we are added to the metal nanometer. So the tin chloride, that is precursors. So once we are added to the tin chloride, it is the formation of the complex. So then it is that indicates to the so milky white precipitation. That okay, precipitate were collected by the centrifuge 30 minutes, remove the impurities, and we are collected that fine pellets. Then we are calcinated at different temperatures, that is 200 degree and 500 degree and 800 degree for the synthesis of the tin oxide nanomaterial. Yeah, next. So this is the formation of the tin oxide nanometer by the UV visible analysis. So UV visible analysis, the formation of the nanomaterial identified. The lambda maxima is 200 nanometer, 275 nanometer at lower temperature. At higher temperature, it increases the visible region. This is the band gap energy of the tin oxide nanometer. While we are looking for the lower temperature, it is shows the band gap value, so 2.68 electron volts. But we are but in the case of higher temperature, that is 800 degrees centigrade, so tin oxide nanometer band gap is 3.14 electron volts. Yeah. So this is the XRD pattern of the tin oxide nanomaterial. So XRD pattern, we are confirmed the formation of the nanomaterial by the best technique for the powder XRD. So material, whether it is phase formation or not, we are checked. So phase formation or whether it is crystalline nature, or we are going to check by the powder XRD. So while looking for the lower temperature, it is shows the 3 Miller indices. While looking for the higher temperature, so multiple Miller indices. So that is temperature increases from 200 to 280. So crystalline nature, it is increased. Yeah. This is the tin oxide nanomaterial. So tabular column of the XID. So temperature at is 200 degrees is the average crystalline size calculated base equation D equal to 4 nanometers. That is less than 5 nanometer. But we are looking for the higher temperature, that is 800 degrees. Average crystalline size is it is less than 15 nanometers. That is 14 nanometers. So temperature increases from 200 to 800 degrees. 200 to 800 degrees, crystalline size was increased. Yeah, next. Yeah, next. So this is the Fourier transformation, FTIR analysis of tin oxide nanomaterial. So here, so this is the plant extract. So initially A, it is responsible for the plant extracts. B and C and D are responsible for the tin oxide nanomaterial. While we are looking for the plant extract, it is shows the multifunctional groups in the plant extracts. while looking for the 10x nanometer, so there is no functional group. Only it is a high intensity. It is peak. It is that is 10x nanometer. So, but in the case of at lower temperature, it is shows the few functional group on the surface of the material. But higher temperature, there is no for surface in the functional group in the nanomaterial. Only it is pure 10x nanomaterial. So that is the confirmation of the 10x nanometer for the FTI analysis. Yeah, next. The transmission electron microscopy TEM analysis. So TEM analysis would identify the formation of the TEM identify the particle size and the shape of the nanomaterial. So what kind of shape is there? Whether it is spherical nature is there, a square type is there, a rectangular is there. So what kind of it is morphology we are going to check for the TEM analysis. It is shows the clear the TEM images. It is the spherical nature. So less than 5 nanometers. So like a quantum dot it is showing. So but here it is F represent for the histogram of the particle size distribution. So this is the 3.9. This is 3.94 equal to the 4 nanometer. So at 200 degrees. Yeah, go for the next. Yeah, TEM analysis at 500 degrees, it is shows the particles as clearly somewhat visible. So average particle size is, average diameter is 8 nanometers. Yeah, next. Yeah, so TEM analysis of 10x nanometer at 800 degrees very clearly shows the particles. We can see it is clearly visible of the particles. It is spherical nature, and average particle size is identify the histogram, that is average diameter is 13 nanometers. But we are looking for the D, it is shed pattern. Particle it is this is the responsible for the Miller index. Each ring it is responsible for the polycrystalline. So circular dots at rings are circular rings, circular spots, which is responsible for the polycrystalline nature of the material. Yeah. Bed surface area. So best surface area, it is identify the bed analysis, identify the surface area. So how it is surface area of the material. So by looking for the lower temperature, this is 153 meters per gram, but high temperatures, so surface areas decreases because it is lower, smaller size of the nanometer, higher surface of the material. Yeah. So photocatalysis analysis. So synthesized material, we are going. We did application of the photocatalytic for the removal of the dye degradation. So here we are using for the multi-lamp photoreactors for the photocatalytic degradation by using UV UV radiation for the degradation of the methylene blue. The case of so 10x nanometer. So in the case of 10x, the visible light, it is gradually decreases the absorbance values. So it is shows the 30 minutes it is degrades of the dye molecules. So then at higher temperature, yeah. So while looking for the third materials, that is higher temperature nanomaterial, we are inside at 800 degrees. So methylene blue, it is degrades within 80 minutes because it is smaller size of the material, so very good for the photocatalytic activity. So that is for the 30 minutes degradation, and percent of the degradation also we are calculated. So this is the response for the percent of the dye degradation. So while looking for the lower and the high temperature, it is shows the very good for the photocatalytic dye degradation for the removal of the dye molecule. Yeah, next. Yeah. So another weird aspect in this for the photocatalytic. So MO methyl orange dye degradation. So methyl orange dye degradation, it is shows the at lower 10 nanometer at lower temperature, it is shows the dye degradation. It is 40 minutes it degrades. While looking for the absorbance value, gradually decreases in the high temperature. That is dye molecule, it is degraded within 100 minutes. But in the case of it is without catalyst, there is no degradation. But in the presence of catalyst, this is gradually percent of removal of the dye degradation. Yeah, next. Photocatalytic. So this is photocatalytic of the tenoxane and for the so effect of the catalyst and the effect of the dye molecules. While looking for the effect of the catalyst, so 10 mg to 30 mg we are applied for the removal of the dye molecules. While looking for the temperature, while looking for the amount of catalyst increases, amount of the catalyst increases, degradation of the time. So degradation of the time it is increased, degradation of time decreased, and percent of the removal it is increased. And in the case of concentration of dye increases and degradation time was increased. So that means it is, so while looking for the 15 ppm, so that is 80 minutes it will take, but 5 ppm it is so that within 20 minutes it is degraded. Yeah, next. Yeah, this is the tabular column of the effect of the dye and the effect of the catalyst. While looking for the effect of the catalyst and degradation time was it is increased and rate constant was increased. So while looking for the concentration of dye concentration it is increased, and percent of the dye degradation it is decreased, and rate constant was increased. Yeah. Next. This is the possible mechanism of the dye degradation. So while material bombarding with the UV light, so electrons transfer from the valence band to conduction band. So conduction band electron captured for the oxygen molecules in the environment. So then it is from the superoxide radicals. Then valence bond electrons captured for the water molecules the hydrogen radicals. While looking for the here higher electronegativity having positive charge, it is stable. But in the case of high electronegativity, it is having the negative charge, it is highly reactive. So then this, okay, so hydrogen radicals and superoxide radicals readily react with the dye molecules and degrades the dye degradation. Yeah, next. This is the conclusion summary. So this is the first time reported for the synthesis of tenoxane nanomaterial by using the cotton plates extract for the photocatalytic. So TEM and XRD reveals synthesize the tenoxane nanometer. It is crystalline nature and average crystalline size, average particle size is 4 nanometer and 8 nanometer and 30 nanometers. This is the synthesized tenoxane nanometer, very good for the photocatalytic degradation. Okay, so this is the outcome of the result. We are published the this part of work, so ACS omega with impact factor, so 4.13. So these are the authors. Okay, so this is my postdoc. During my postdoc, we did this work. Yeah, next. Okay, so this one more interesting topic. It is grass. So we are developed the material with grass that is completely agro waste. So this is the grass. So that what is that grass? So actually it is darva grass. Darva grass it is in the agriculture material. So this is the cotton plants. So this material completely it is grass. Once it is crop in the agriculture field, so there is no growing of the plant. So this growth morely effective in the agriculture crop. So that reason we are looking for the agro waste. So this grass were collected and make it into the powder. So then powder we are going for the analysis. So what are the function of the really it will work for the synthesis of nanomaterial or not? We did actually. So we checked. So it is successfully synthesis of the nanomaterial. It is working. So then next. Yeah, so that agro waste material we are used for the synthesis of the titanium dioxide nanomaterial. So titanium tetraisoperoxide dissolved in 30 ml distilled water. So gross aqueous extract, we are making the aqueous extract. Gross was collected and make it to the powder. So that powder it is dissolved into the dissolve into a double distilled water. Then we are heated to the then we heated so that whatever it is phytochemicals dissolve into the water, then filtered with micro filter paper. That extract used for the synthesis of the nanomaterial, that is 10x nanomaterial, were added to the drop phase. While we are completely poured into the that metal solution, it is form agglomeration. It will be develop the bulk material. It will form. So that reason we are added to the extract. So slowly we are going to add. So that use peristaltic pump. So that means drop we are added to the extract to the metal salt. Then it is form the fine particles. So that reason we are added to the using peristaltic pump. So after that, once it is formation of the that whatever it is phytochemicals, then it is formation of the metal. Complex it is formed. Once it is complex it is formed, that means precipitates it is formed. Carefully precipitates were collected. So that carefully collected by centrifuge, carefully collected and dried at room temperature. Then we are make it to the fine powder. That powder we are going to the calcinate at a different temperature. That means 200 300 degrees and 500 degrees and 800 degrees. So then we are collecting the material, we are stored that fine powder. Okay, that powder we are going to analysis for the different analytical advanced analytical instrument. So that means powder XRD and TEM analysis and bet analysis. For the bet analysis, we are surface of the material. For the TEM analysis, we are particle size. What is the size of the material? We are identifying. XRD, powder XRD, it is crystalline nature. Whether it is forming or not, we are going to identify. So best technique is powder XRD. Whether so for the organic people, best technique it is NMR. But for the material chemistry, best techniques primary technique it is powder XRD. Yeah. Next. Uh, is it my voice? It is audible, sir. Somewhat big. Hello. Is it audible? My voice, Professor Albino. Professor Albino, your mic it is off. Mute. Mute. It is audible. My voice. Hello. Yeah. So this is okay. So UV visible analysis of the titanium dioxide nanomaterial. While titanium dioxide material at lower temperature, 326 nanometer, but higher temperature, so it is 355 nanometer. So temperature increase from the visible shift it is toward to the visible. This is the D representative for the band gap energy. Band gap energy was calculated by dot plot equation. That is at 200, 300 degrees. It is 3.01 electron volts. At 500 degrees, band gap energy is 3.15, 18 electron volts. At 800 degrees, band gap energy is 3.23 electron volts. Temperature increased, band gap was increased. So that is means regular arrangement of the atoms. That may be crystal defect. Okay, next. Yeah, so this is the powder analysis of 10x nanometer at lower temperature and higher temperature. This is the response for the so without a calcination. So that material as a synthesized material. So while we are check for the powder XRD analysis, there is no fire formation, but we are looking for the 300 degrees, very fine Miller indices, very fine peaks. So that is the formation of the nanomaterial, titanium dioxide nanomaterial. At higher temperature, very fine sharp peaks. That is very good crystallinity of the material, crystalline nature. This is the responsible for, yeah. So another also we are compared with the commercial titanium dioxide nanomaterial. Commercial titanium dioxide, how it is higher temperature, look like that. So this is the titanium dioxide nanomaterial. At lower temperature, it is debased Kircher equation. We are debased Kircher equation for the crystalline size 5 nanometer. At higher temperature, 800 degrees, the debased Kircher equation. Okay, this is the 25 nanometer. But in the case of commercial titanium dioxide P25 nanometer, that is 84 nanometers. Yeah. Tin oxide nanometer at lower temperature to shows the particles are spherical in nature. This is the responsible for the F elemental of the composition, whether really thin material is there or not. E represents for the set pattern of the material. So D represents for the D spacing. So one plane to one plane. So how much distance is there? So that also we are identify the TEM analysis, which is responsible for the, it is closest to the XRD. So XRD result. Okay, that is the where confirmation of the tin oxide nanometer by the TEM analysis. Yeah, next. So here, so titanium dioxide nanometer at 500 degrees centimeter, it is identify the average crystalline size. It is less than 10 nanometers. But okay, here we can see here at higher temperature, it is bright circle and spotted dots. That is the polycrystallination of the material. We are confirmed. Yeah, next. Yeah, titanium dioxide nanometer, and also we are confirmed with dynamic DLS analysis and TG analysis. From the DLS analysis, whether it is a solution state stable or not, we checked. At TG analysis, thermally whether it is stable or not. While looking for the DLS analysis, dynamic light scattering. So that is very sharp peak at 300 degrees and 500 degrees. At 800 degrees, very slope it is there. So that means at lower temperature, it is minus 41 point millivolts. At 800 degrees, that minus 33.7 millivolts. It is shows the very good at lower temperature. Nanometer is stable. We are going for the confirm with the standard. Okay, that is the DLS analysis. While looking for the TG analysis, from temperature increases from 300 to 500 degrees, how it is material is weight loss. Okay, so how material is weight loss? So based on that, whether it is thermally stable or not. While looking for the 300 degrees, it is 3% of weight loss. But in the case of higher temperature, it is 0.55, very less weight loss. So initially, this is the weight loss, maybe due to the volatile compounds and any other input is removed. Okay, in this case, after that, so very carbon content it is there. Here, very volatile compound it is removed. Yeah, next. Developed develop the titanium dioxide. We apply for the photocatalysis using multi-lamp photoreactor. It is a closed setup, and inside it is wall is there. So in that wall, we set the visible light or UV light. We are going for the check the dye degradation. Okay, that is closed setup where every 10 minutes we are collecting the material. So that material collecting, we are analysis for the UV journals. That how it is happen. So this is the initially of the dye molecule at 0 minutes, while every 10 minutes we are collecting the dye solution. So we are identify the absorption of the dye molecule, absorption of the dye solution gradually decreases. So that means within 15 minutes degrades. But in the case of titanium dioxide metal, third sample, it is shows the very slow, somewhat it is slow because it is surface of the material, because it is what is it? Nanomaterial, okay, strongly influence of the size of the material and surface of the material. It is strongly influence of the dye molecule. While looking for the lower temperature, that means lower temperature synthesis material, it is shows the very good photocatalytic activity. But in the case of without nanomaterial, so we are added to the just we are passing to the UV radiation. So there is no degradation in the case of first sample and second sample and third sample. Yeah, yeah. But in the case of catalyst, it is gradually okay percent of degradation increased. Yeah, next. Yes, sir. This is same. So photocatalytic of the titanium dioxide for the so another dye. So really it is material worked or not? We checked. So it is shows the so rhodamine is a strong dye. For the of the dye degradation, we are performed in similar way. In the case of okay, so lower temperature that means lower temperature synthetic nanomaterial, it is shows the degradation very quickly. So higher temperature, it is somewhat slow for the completion of the dye degradation. Yeah, next. Yeah, this is the effect of the catalyst and the effect of the dye conversion. So whereas while looking for the catalyst, that means 10 mg to 20 mg or 30 mg. Okay, while looking for the 10 mg, it is shows the percent of yeah. So this is the degradation time. It is 70 minutes. So this is the kinetics plot while looking for the catalyst. So this is also so effect of the dye concentration while looking for the lower concentration. It is a degradation time. It is quick. That means it is the kinetic plus very quickly. But in the case of higher ppm, it is take some time. That means for the removal of the dye molecule, it is going to delay. That it is going to it will take removal of the dye. Required temperature, required time it is more. Yeah, next. Yeah, conclusion. So this so we are developed the tinoxide nanometer by using Darbograss extract. It is useful for the synthesis of the nanomaterial. It is working because we are primarily identify the phytochemicals which is present or not. So that primary phytochemicals responsible for the formation of the nanomaterial. So this is the thing. And for the characterization, we confirm the material. So that is very crystalline nature. So particle size, it is identify the okay TEM analysis. So amount of the catalyst. Once we are sincere develop material for the amount applied for the photocatalytic dye degradation. That is amount of the catalyst increase rate constant of the methylene bromethylene dye is increased, whereas amount of the dye concentration increase, degradation time is more. So this is the outcome of the result. We published SS omega biogenic photocatalyst titanium dioxide nanometer removed of the environmental pollutants. So whatever we are generated data, so that data we are published in this SS Omega in another paper. Yeah. So these are the authors. Okay. Yeah. So go next slides. Synthesis. Another one metal oxide nanometer synthesized by green method. So this is the iron oxide nanometer 0.05 molar iron nitrate salt dissolved in 50 ml distilled water. Then we are added to the extract. So what is that extract? Ecloproducts extract. So plant material. So that extract we are making the to extract, that extract added to the tin salt. So that means iron salts. So iron salt, it is added to the dropwise peristic plum, how we are previously we worked. So then formation of the black color precipitation and centrifuge 5000 rpm 30 minutes. Carefully, pellets was collected and dried at 60 degrees and 3 hours. We get the fine pellets. We are grind it to the make a powder. So that is called iron oxide nanomaterial. Further, we are confirmed for the analytical technique. So whether it is material formation of the iron oxide or not, we confirm. So next. Yeah, so XRD, FT, and UV visible analysis of iron oxide nanometer. So XRD, powder XRD, where confirmation of the nanometer, it is crystalline nature, high intensity peaks, which is responsible for the different Miller indices. So average crystalline size were calculated, Debye Squirrel equation, D equal to 24 nanometers. So this is the plant extract, ecloprax extract, FTAR. This is the iron oxide nanometer. So we confirm the functional group. Yeah, functional group iron oxynometer surface is present. This is the okay, standard JCPDS card number. Okay, we confirmed with whether it is iron oxynometer matches or not. They are confirmed. So this is the X1 spectra. This red lines responsible for the each peak, okay, matches with the standard. That is the iron oxide material. It is confirmed. So further, we are confirmed for the UV visible analysis, formation of the nanometer, each metal having a specific character. So that is the 296 nanometer of the iron oxide nanometer. Yeah, next. Yeah. So this is very good application. So there actually we are looking for the degradation of the by using UV light. But in the case of here, iron oxide nanomaterial, we are for the reduction of the dimolecular. How it will be a reduction? By nanomaterial. By looking for the by sodium hydride, the presence of catalyst, it is captured from the hydrogen to di molecule. Then it is degradation of the di molecule. How it will absorbance value slowly it is degradation. Then Congo red also similar way Congo red also we are checked. So this is also absorbance value. So gradually decreases. That means within 40 minutes it is degraded. That how much quantity we are taking for the dye molecule and how much amount of the added to the catalyst and sodium borohydride. Why we are for the methyl alanine 3 ml of the dye we are taking and sodium borohydride micrometer we are added very less we are added and catalyst we are added 60 microliter per ml we are added. Then we here it is so the degradation time within 10 minutes it is degraded. That means 98% it is degraded methyl. In similar way Congo red is 97% it is degraded. Yeah, next. But in the case of here, one interesting factor it is. So while looking for the sodium barrel without catalyst, there is no degradation. We can see here. So there is no degradation. So dimolecule and sodium borohydride, dimolecule and sodium borohydride. But in the case of catalyst, it gradually decreases. That means that is the motto of the work. Okay, next. Next. Yeah, so this is the possible mechanism, the reduction of the so methyl alanine Congo red. While dye molecule, the presence of catalyst, how it will the reaction happen? Next, front. Front. Next, front. Before slide. No, 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 no. Forward, forward, backward, backward, backward. Backward, backward, backward. Yeah. So this is the iron oxide nanometer. So here, iron oxide nanometer, hydrogen, 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 front. Next slide. Next slide. Next slide. Yeah, wait. So here, iron oxide nanometer, it is hydrogen. It is taking from the hydrogen to di molecules. So that di molecule, it is okay. Hydrogen di molecule, it is due to the degradation of the azo bond. So that means azo reduction. So hydrogen molecule, it is hydrogen molecule is a reduction of the di molecules. Here without catalyst, barrier center it is decreased. So that material, iron oxide nanomaterial, it is barrier center, it is decreased. But in the case of without catalyst, there is no hydrogen transfer. So that means diminishing the activation energy, di molecule and iron oxide nanomaterial and sodium borohydride. That means sodium boro di molecule, it is reduction of the di molecules, then degraded of the azo bond, then it is form smaller entities. So that means leucoformation. That is the concept of the how it will work, the reduction of the di molecule, that in the case of iron oxide nanomaterial. Yeah, so this is one another aspect of the metal oxide nanomaterial, zinc oxide nanomaterial. So zinc oxide nanomaterial, so zinc acetate dissolved in the distilled water, then we are added to the extract, that is Tirpala Chopana extract. We are making the extract and then we are added to the metal salts, then formation of this brown color precipitation, then it is centrifuged. So calcination at 500 degrees and 3 hours, we get the zinc oxide nanomaterial. Next. So here green method were developed by plant extract. Yeah, next. Yeah, so chemical method. So XRD pattern of the zinc oxide nanomaterial, green method and chemical method. While we are looking for the green method, it is the XRD pattern of the zinc oxide nanomaterial and diameter is crystalline size, it is 30 nanometer. While looking for the chemical method, so average crystalline size was increased. See here, green method, it is less than 15 meter, but in the case of chemical method, it is 34 nanometer. It is large changes of the size of the material. So that is case where compared with the chemical and green method at similar condition. Yeah, next. So this is the tabular column of the zinc oxide nanometal, chemical method and green method. While looking for the green method, average crystalline size was calculated by Debye-Squirer equation, that is 13 nanometers. So this is the chemical method. So zinc oxide nanometal, where average crystalline size was calculated by Debye-Squirer equation, D equal to 34 nanometers. This is the lateral planes and beta value, full width of action. So full width of it is increases, but chemical method it is more, it is decreased. Yeah, next. Yeah, so irreversible of the zinc oxide nanometal, chemical method and green method. While looking for the chemical method, this is the plant text of the UV analysis. It is shows the absorption band and 2 it is there. But in the case of only material, that is chemical method, green method, it is shows that each metal oxide specific character of the absorption band, that is 343 nanometers. While looking for the chemical method, it is 355 nanometer. This is the band gap of the chemical method and green method. While looking for the chemical method, it is band gap energy 3.04 electron volts. While looking for the green method, so band gap energy is 2.86 2.86 electron volts. So this was calculated by Debye-Squirer equation. Yeah, next. TEM analysis of the zinc oxide nanometal at green method. While looking for the green method, it shows the particles as very safe, very clear, and spherical in nature. And C represent for the center planar distance of the one interplanar distance of the material. So that means 0.24, which is good agreement with the XRD result. This is the D represent for the set pattern of the crystalline polycrystalline nature of the material. So F represent for the E represent for the element analysis of the zinc oxide nanometer. So F represent for the histogram of the particle size distribution. So average diameter is 14 nanometers. Next. Uh, this is TEM analysis of zinc oxide nanometer at 500 degrees with chemical method. While looking for the chemical method, it is square type. It is square type with the nanometer. We can see here a square type. We can see here a square type. But in the case of green method, spherical in nature. In chemical method, how it is morphology change because of the chemical method. It is strongly influence of the morphology of the material. This is the D represents the said pattern of the material. It is shows the polycrystalline nature, and F represents for the histogram of the particle distribution. It is shows the average diameter is 26 nanometers. It is very close to the XRD result. Yeah, next. Synthesizer chemical and green method were applied for the photocatalytic activity. While looking for the green method, zinc oxide nanometer at 10 ppm, it is volume it is taking for the 70 ml, 20 ml catalyst, and visible light. It is bombarding with the visible light. It is degraded within 100 minutes. Within 100 minutes, with UV methylene blue. While looking for the chemical method, methylene blue, it is shows the 150 meters gradually decreases the absorbance value. So that means developed green method strongly influence for the photocatalytic of the dye degradation because is a smaller size of the material. Yeah. So next. So this is synthesis of zinc oxide nanomaterial through the chemical method and green method, then environmental pollution for the remediation. This is manuscript. It is preparation, under preparation. So actually, I asked to sir, we can go for the make it for the paper some for the expenditure for we can complete the this paper. I hope I asked to the Professor Albino, will complete this work. We can go for the publication. Okay, further. Yeah, next. Conclusion and summary. So successfully synthesize the metal oxide nanometer, that is tin oxide nanometer at different temperature, and titanium dioxide nanometer at different temperature, successfully synthesized and applied for the photocatalytic effect, and very good for the dye removal, and we published these two papers in ACS, and this is the iron oxide nanomaterial also. I'm preparing for the manuscript. So iron oxide nanometer for the reduction of the dye azo dyes. And another aspect is zinc oxide nanometer chemical method and green method. This is also under review. This is also we are making the manuscript. So I hope some fund we are needed for this. Completion of the work. So that's what I am requesting for the Professor Albino. So completion of these two going to the publication. Yeah. So this is our metal oxide nanometer, how it is synthesize the material through the green method and chemical method. So how it is act for the photocatalytic degradation. So majorly it is go for the band gap the material and especially it is material for the band gap of the material and size of the material and morphology, how it will work for the photocatalytic activity. So this is the concept of the metal oxide nanomaterial. Okay. Yeah. Thank you very much for all. So it is lot of trouble. Last time also it is bad connection. So that reason heavy rain. So I couldn't present last time, and this time also more taking so bad connection. With patience, you are attending the my presentation. Thank you very much for all. Thank you lot. Questions we can make a rise. Thank you very much, sir, Professor Albino, Professor Angelo Bostumana. So to providing a good opportunity to me in the last couple of last year and before last year. Thank you very much.
Okay.
Yeah.
Can you hear me?
Yeah, yes.
Thank
Sir.
you, Dr. Narsi, for your very interesting talk. It's hard work, lot of data to analyze, and I will not ask a question now. I'll ask people if they have questions. Okay?
Yeah.
Can you?
Yeah.
Let's start with Professor Angel Bustamante.
Obrigado. Professor Narsi, in your iron oxide magnetite, it's possible to show the lamina to slide.
Which one,
Yeah.
Angel?
No, I don't know what is the number. It's the
Vamos a ver.
magnetite. The
Magnetite.
Magnetite.
See, because I have to see one sample, one is pure or have to magmite.
Yeah.
Because the peak 511 is important.
Iron oxide nanomaterial. You are asking, right?
No, diffraction X-ray spectra de
X-ray.
nanoparticle magnetite.
Yeah.
No. Look at this.
This is not magnetite.
No, this is not magnetite. No.
Let us go there.
In magnetite, there is a peak.
We will reach it.
511.
511. Yes. So iron oxide nanomaterial.
Yeah. This peak is important for because there is a magmite también have to equal peak.
This is the X-ray.
Yes. 511.
Yeah. Maybe 511.
Yes.
Amplia. There is you como amplifique la lámina. It showed the 511 because this has two asymmetric peak. Then you have magnetite, you have to magmite.
Okay.
Look at this.
Yeah,
you amplify this. 511. It's possible to amplify the lamina.
No, let me see.
Yes, I got.
Yeah, sure.
Maybe
sure.
Echo. Yeah, yes.
Yes.
You have asymmetric peak. You have a symmetric peak and it's 511. Then you have to magnetite and iron oxide magmite. No, it's very, o sea, no es only one sample,
because it is we are using for the
maybe
exactly.
No,
yes, exactly. Because we are using for the plant extracts. So that material, it is making some noise, but we are more several times we can, okay, so we can wash, okay, we can get the clear, okay, magnifies.
Okay.
So then sure it is possible. We can magnify. Some noise is there. Yes. So we can several times we can wash that material. So sure it will magnify. Clear it is peak, it will come. Yes.
Yeah.
Claro. You need to put a use when using two Gaussian line. Maybe to have two areas, the magnetite and magnetic. Maybe, no sé, pero need to show the one sample. Muy bien, thank you.
Yeah. Okay, thank you, sir.
Gracias. Thank you, Professor Angel, for your questions. Now I will invite Professor Stuart Holmes. Stuart, are you there? Okay.
Thank you. Thank you, Dr. Boya, for your presentation. I think I got most of it. I just have a general question. So you said in your introduction that nanomaterials were useful for, say, solar and photovoltaics.
Okay.
In particular, you mentioned the tin oxide. What aspect of the tin oxide would be useful for solar? Is it as a contact?
So
is it as an electrode, a large area electrode? What aspect is useful for solar or photovoltaic?
So tin oxide nanomaterial, especially it is used for the photocatalysis. So that tin nanomaterial, so especially so that band gap less than 3 point electron volts. So that band gap value, so it is strongly influenced for the photocatalytic activity. So that reason we are looking for the tin oxide nanomaterial, and with lesser size, and with that lesser size, so it is more effective for the photocatalytic activity. So that reason, especially we are looking for the tin oxide nanometer. Of course, so you are correct. It is used for the some energy related, that also it will work. So that reason, especially in this reason, band gap energy, it is getting lower. So that reason we are looking for that material. It is applying for the photocatalytic activity. So that is the reason.
Thank you. Very, very interesting talk. Sorry to have the problems with the presentation, but very, very interesting. Thank you again.
Yeah. Yeah, please, sir. Any other questions? Hello? Hello? Yeah, Professor Albino.
So, Sergio, do you have a question?
Okay. So, yes, I have thank you very much for your presentation, Dr. Narsi. It was very interesting, so I really enjoyed it, despite the fact that we started very late. So can you hear me?
Your voice.
Can you hear?
Can you hear me, Albino?
Yes, I'm hearing you.
Yes.
Dr. Narsi, can you hear Professor Sergio?
There is no audible. There is no audible. Question, there is no audible.
Sorry, can you hear me now?
No audible.
No, you can't, I think. Okay, can you hear me now? Hello? Hello, can you hear me?
Check my mic?
Sorry, Albino, I think he's not hearing.
Narsi, can you hear me? Narsi? Narsi, can you hear me? Can you hear me? No. That's bad. Lot of problems today, Sergio.
Yes.
Narsi, can you hear? Check your earphone, please.
Can you hear me?
No. Let me. Yeah, this is problem.
Professor Albino? Professor Albino?
Yes. Yes, can you hear me?
Professor Albino?
Hello?
Can you check my...
Hello, Narsi, can you hear me? Narsi? Can you hear me? Sergio, can you hear me?
Yes, I can hear you, Albino, perfectly.
No. I don't know how to proceed. Let me stop you now. Narsi. Hello, Narsi.
Hello? Hello? Hello?
Hello, we can hear you.
Yes, sir. So audio not working.
Can you hear me now? Okay, Sergio, can you try to see if he can hear you?
Can you hear me, Dr. Narsi? I think, Albino, the problem is with Dr. Narsi.
Yeah, I think so. Let me ask him to. Let I see.
Hello?
Hello?
Hello? Hello?
Hello?
Hello.
Can you please check once again?
Can you hear me, Dr. Narsi?
Audio not working.
Can you hear me?
Narsi, can you hear? No. Let me. Let's see if he connect. What happened if he connect again?
Okay.
Quando ele conectar. Bueno, está muy difícil, ¿no? Es una charla muy interesante. He's coming. Let us see. Dr. Narsi, can you hear me? Your microphone is off.
Yeah.
Can you hear me now?
Yes, yes, sir. Please say.
Yes.
Yes,
okay,
sir.
so thank you very much for your very interesting talk. So I really enjoy it.
Thank you, sir.
My question is, have you tried theoretical or computational approaches such as density calculations to get better understanding of your experimental results?
Okay. Yeah, thank you, sir.
Narsi, did you hear the question of Professor Sérgio?
Yes.
Did you try a computational approach to analyze your results? Is that the question, Sérgio?
Such as density calculations for getting a deeper understanding of your experimental results. Have you tried theoretical or computational approaches to match with your experimental results?
Yeah, so computational we can apply. Yeah, I will try this. Computational still we didn't try this computational actually. Hopefully, I will make this computational for the result. Whatever we are getting that result, okay, we can apply that. Sure.
Okay, so I have another question. So you're working on doing the synthesis of nanoparticles to for photocatalysis applications. So for mainly from getting pollutants, right?
Yes,
but the photocatalysis principle is the same for hydrogen production. So because you need to have the valence bands and the conduction bands aligned to the redox potential for the chemical reaction that you want. But have you tried this kind of material for hydrogen production?
Yes, sure, sir. Because next topic it is our actually that hydrogen production only. So this it will work for the hydrogen production, semiconductor material. So that means water splitting. So
water splitting, yes,
sure.
yes,
water splitting. So it will work very good, sir. So so that work also it is going on. So once we will apply for the hydrogen generation also. Very good application actually that is current trend. So especially in foreigners, mainly it is photocatalysis. It is applying for the hydrogen generation. Yeah, that is very good, interesting topic also. So sure. So this will definitely it will work for the hydrogen of generation. Yeah. So I have a basic idea for the hydrogen generation, water splitting. So sure, sir. If you give good opportunity, definitely I will work in that this area, hydrogen generation also.
Yes, you can also apply this kind of material for CO2 reduction, for making methanol or another kind of.
Yes, with methanol. Yes.
Yes, it's quite versatile the photocatalysis area. So thank you very much for your very interesting talk.
Thank you very much, sir. Very valuable suggestion. Yeah.
Gracias, Sérgio. Thank you, Sérgio, for your contribution. Now I would like to ask Arturo Martinez. Are you there?
Yes.
Good
morning.
Arturo? Okay.
Yeah. Good morning.
I have only one question. Many thanks for your talk.
Yeah, thank you.
But, what is the maximum amount of the synthesis of the powders? I think kilograms or only grams.
Yeah. So only grams, 50 mg. We are getting for the one cycle 40 mg or 50 500 mg. So small scale we are developed actually. So that means nearly to the grams only, not big scale. So if it is, we can make a bulk also. We can make But for the research scale, very less we are making, sir. So it will, we can make big also.
Okay.
Big amount of
many thanks for your talk.
Yeah, thank you, sir.
Thank you, Arturo, Professor Arturo, for your contribution. Let me just a minute. Who are more in the Sérgio, Albino, Stuart, Creseu, Ximena, still there?
Sí, profesor Albino.
Question from the students?
We don't have questions here in Colombia from our students, but they only say thank you for your talk. And, well, sorry for the problems in the start.
Yeah, thank you, madam. So initially it is more trouble. Thank you.
Thank you, Ximena. Let me see. Cecil, do you have any question from people? Low?
Hola, profesora. Saludos. No tenemos preguntas por aquí, solo agradecimiento por la presentación.
Gracias, Cecil. Thank you. Antonio, you are there? Still? No. So, back to me. So, Dr. Narsi, thank you very much for your interesting talk again. And sorry for these problems we had to start.
So, I'm sorry for the, actually, it is a big bad connection. So that reason, so that reason it is going delay.
Before finishing, I would like to ask you.
Last time also it is a big problem, heavy rain. It is delayed, and this time also it is a bad connection. Once again, thanks. Once again, sorry for that delay. So thank you very much. Yeah, please, sir.
My question is, how difficult, back to the Professor Arturo question, how difficult it is to move from grams to tons?
Okay. So material we are developing this, we are using very less amount. So that means precursor we are using, that is that means 0.5 normal molar. So we are working material, we are taking the precursor, it is more, how much it is required for the reduction of the material. So based on that, we can calculate and we can make a bulk amount of the material. It is possible because it is we are making the laboratory. So laboratory we are using for the analysis, we are making just mg or grams. So we are making the some big amount of material, so it is possible.
Okay, thank you. Before asking you to go for your final words, let me mention again that this network, the Latin American Network on Condensed Matter Physics and Material Science, is formed by several universities and institutes. And we have the University of Nacional Maior de São Marco, de Lima, Universidade de Barranca, também em Peru, Universidade Nacional de Colômbia, em Bogotá, em Barranquilha, Universidade de Zulia, na Venezuela, o Sinvestaf, no México, nós temos a Universidade Católica do Norte, em Chile, a Universidade Federal Rural de Pernambuco e a Universidade de Pernambuco e a Universidade Federal Rural do Rio de Janeiro, no Brasil, e a Universidade de San Martín, na Argentina, a University of Cambridge and the University College of London, in England, a Universidade de la República em Uruguai, es muitas. Bueno, entonces essa es this is how it's composed, this LAFMAT, and we try to put people together to work and discuss. And today we have a very, very interesting talk from Dr. Narsi Boya. And with this, I would like you to say your final words. Narsi?
Yes, sir. Thank you very much for all this providing good opportunity to me. I request to the Professor Albino. So the application, it is under process. So I hope, okay, so I request to Professor Albino to process my application for the postdoc. Okay, so this is very good opportunity to me. Once again, thanks to the all to attending this topic, that is nanomaterial. Thank you very much for all this giving good opportunity to me. Thank you very much. Thanks for all.
Okay, thank you again, Dr. Narsi. Thank you to everybody for joining for this meeting today. And I think now we can conclude saying that, Cecile, can you stop the record? Stop recording and say, please open your camera to say bye-bye to Dr. Okay, now, bye.
Thank you again.
Yes. Thank you.
Thank you. Bye.
Bye. Bye-bye. Ciao, ciao.
Bye.
Ciao, ciao.
Hasta luego a todos.
Ciao. Ciao. Okay. Let's close it. So bye. See you.